In our tank example, we've now seen that we can predict into the future and get the predicted chemical levels or chemical amounts simply by taking our initial amounts in each tank and multiplying those amounts with matrix multiplication with n times our transition matrix A, or our transformation matrix A, or we could write that as a to the nth power. However, we see that when we are trying to compute a to the n times a vector, there's two ways that can go. If we have v, which is not an eigenvector, then if we want to calculate a to the n times v, then what we have to do is do our 0.9, 0.1, 0.1, 0.9, multiply that out by the same matrix again, on 0.1, 0.9, and do that potentially hundreds, thousands, there's no reason why we'd want to limit ourselves, a large number of times, and that is, as we indicated earlier, long and tedious and, in scientific terms, icky. Let's contrast with the case where v is an eigenvector. Well, then we know from the eigenvector equation that a times v is lambda times v, and we saw in an earlier example that if we take the nth power of our transformation matrix A and we multiply it by these special directions, then we just get lambda to the n times v, and we're done. You want to know what the nth power applied to that vector is? Just take the eigenvalue to the nth power and you're done. Multiply it, scale it by that. And that is so much easier if we use the right vectors. Now, we're given some vectors, so we'll have to work around that, but maybe a better way to say this is by choosing the right basis to express our transformation in, we can make it really simple. We can replace complex multiplication of matrices with simple multiplication of scalars, but only if we take our building blocks being the vectors that sort of fit the system. If we just leave it as xy, like we started with here, then life gets pretty messy pretty quickly. So with that, we definitely have an incentive to get the eigenvalues and eigenvectors for A. So we're going to recap our approach for this, and we're going to do this, relatively efficiently. We have the eigenvalue condition. Again, you should try to restate this in your own head as you're going here. We have a matrix. What's the condition on the eigenvalues? Well, it always hinges on this A minus lambda I form, and the eigenvalue condition is that the determinant of that matrix equals 0. And what we're going to do is 9/10, 1/10, and you could keep this as decimals if you like. I'm just more used to fractions when it comes to these kinds of calculations. We're taking the determinant of a 2 by 2 matrix, negative lambda down diagonals from the minus lambda i's, and so we get a product down the diagonal of 2 9/10 minus lambdas, and then minus, that's 1 over 100, or we'll write it out, 1 over 10 squared, 1 over 110, 110. And then we want that determinant equal to 0. Now we expand this out, and we get ourselves 9 is 81 over 100. Then we have minus 9/10 is minus 18/10, lambdas and a lambda squared, minus 1 over 100. So we'll then tidy that up and put the lambda squared first, minus 18 over 10 lambdas, and then plus 81 minus 1 is 80 over 100. And what can we do with that? Well, there's two things we can do. First off, we can cancel out a 0 here, so it's 8 over 10. And then what we're going to do is multiply this whole thing by 10 just to get rid of these horrible fractions. So 10 lambda squared minus 18 over 10, but times 10 is minus 18 lambdas, and plus 8 equals 0. Now that's a much nicer quadratic. What are we going to do with that? Before we use the quadratic formula, let's just do one last division because all of these are even, so we can divide by 2. And I think, yeah, 2 is as good as it gets. So 5 lambda squareds minus 9 lambdas plus 4 has to equal 0. And at that point, we pull out our quadratic formula, and we get that lambda is minus 9, so 9, plus or minus the square root of 81 minus 4, 5, and 4, all over 2a. This leading term is 9/10. We have 9 over 10, plus or minus over 10, the square root of 81 minus, oh, that's 80. We have 20 times 4 is 80. So that's 81 minus 80, that's just 1. Hey. That's 9/10 plus or minus 1/10. And if we do the addition, we're going to get 10 over 10, which is 1. And if we do the subtraction, we're going to have 8/10. Those are the eigenvalues of A. Eigenvalues of A. All right, next up, our calculation of the eigenvectors. So for lambda equals 1, and call that lambda 1, remembering that our eigenvector condition is that the A minus lambda I now times a vector has to equal the 0 vector. And we set up that condition for each eigenvalue separately. So we're going to take our A matrix here, and this time I'm going to do decimals. I think it's easier. Minus 1, 0.9 minus 1, and 0.1, 0.1. And let's let our V vector here, we don't know what it is, let's give it two numbers, A and B. And I just realized I want a bit more space around this, so I'll shift this down a hair. There we go. This has to equal the 0, 0 vector. And if we do the scaling we get with this, we get negative 0.1, 0.1, 0.1, and negative 0.1. AB equals 0, 0. And we do a little check here that this matrix here is not invertible. And that's exactly what we want. The two rows here are just negatives of each other. And so what we can do is just pull either row that we like. I'm going to pull 0.1a minus 0.1b's, the second row multiplying the vector, equals 0. And we bring this over, multiply by 10, you just get that a equals b. So now we have our picking thing. We can pick, say, a equals 1, b equals 1 then. So our vector is the 1, 1 vector. And that's for our lambda equals 1. And now we repeat for lambda 2, which was our 0.8 eigenvalue. We build our matrix 0.9, 0.9, 0.1, 0.1, copying this matrix here, and then we subtract down the diagonals. And we take that matrix, we multiply it by our AB numbers that we're looking for, and we set that equal to 0. We need to tidy this up though first, so we get 0.1, 0.1, 0.1, and 0.1 again, times AB equals 0, 0. Again, we have that check. It is not invertible. These rows are just the same rows over and over again. And so we just pick either row. We get 0.1a plus 0.1b equals 0, scanning that out. And then last but not least, we multiply by 10 and bring this over the other side. And here we can start picking. Let's pick b equal to 1. That will immediately give us a equals negative b, which is negative 1. So our vector for this eigenvalue is A first, then B, and just to keep the nomenclature consistent, this vector goes with that lambda, and this vector goes with that lambda. And those are the eigenvalues and eigenvectors for our matrix A.